Welcome to the Chemistry, Biology and Math Revision Hub. Today we're doing the Pearson Edexcel International A-Level Chemistry Unit 3 for May 2024. Let's begin with the first question. In question 1, this is a question about practical activities involving the collection of a gas. A student used the apparatus shown to collect the gas produced from the reaction between copper 2 carbonate and sulfuric acid. Of course, this reaction produces carbon dioxide gas, which is going to be collected over water, as we can see here. The reaction takes place in this boiling tube. There is a rubber band to prevent escape. A delivery tube takes the CO2, and this is going to displace the water as it goes above the water. So the disadvantage of this method is that some of the carbon dioxide could dissolve in the water, and the volume collected may not be representative enough. Usually, this method is used when the volume of gas produced is so much, so the tiny volume that dissolves is going to be insignificant. They say the bank was removed and 0.650 grams of copper 2 carbonate was added to 25 centimeters cubed of 2 mole per decimeter cube sulfuric acid, which is an excess, in the boiling tube. The bank was quickly replaced and 120 centimeters cubed of carbon dioxide gas was collected in the measuring cylinder. The equation for the reaction is shown here. We can see this is the mass of copper carbonate. We have sulfuric acid volume in concentration. Of course, this is an excess. And then the volume of CO2, which is 120 centimeters cubed. They say calculate the molar volume of carbon dioxide gas in decimeters cubed per mole from this data and give your answer to an appropriate number of significant figures. So since this is excess, I'm going to use the moles of copper carbonate. So number of moles of copper carbonate will be 0.650, which is the mass, divide by the molar mass, which is 123.5. And I got 5.2632 times 10 power negative 3, and that is moles. When we look at the mole ratio, it's 1 to 1. So the moles of copper 2 carbonate are going to be the same moles of carbon dioxide gas, which is that. And so using this formula, number of moles is going to be the volume of gas produced, which is 120, divided by molar volume. The molar volume is going to be the volume of gas, which is 120, divided by the number of moles. Of course, I converted this volume from 120 centimeters cubed to 120 times 10 power negative 3 decimeters cubed. And my answer was 22.8 decimeters cubed per mole to 3 significant figures. In part B, they say after the reaction, tests can be carried out on a mixture to show that the sulfuric acid was in excess. State the observation if a small volume of sodium hydrogen carbonate solution was added to show that the acid was in excess. If the sodium hydrogen carbonate is added and there is an acid or H+ ions, effervescence is going to occur as carbon dioxide gas is going to be evolved, so the observation is going to be effervescence. And next they say describe a different test and a positive observation that could be carried out to show that the acid was in excess. Of course, you can use blue litmus paper. It's going to turn red, or you could use universal indicator paper. And in part C, they say another student used the apparatus shown to collect the volume of gas produced from the reaction between a group 2 metal carbonate and excess hydrochloric acid. Now we can see this is a different collection method because they are using a syringe. Using a syringe gives better results because the gas is not going to dissolve in water. So they say give 2 reasons why the second set of apparatus gives a more accurate measurement of the volume of gas given off, and they want you to justify your answer. Like I said already, a gas syringe is used to collect carbon dioxide, so a more accurate volume of CO2 is collected here, and some CO2 dissolves in the water in the first experiment. I already talked about that. In the first setup, some carbon dioxide gas escapes before the bang is closed, and the syringe has more divisions, so it's going to measure even smaller changes. We can see the gradation or the tiny graduations onto the syringe are more, and so even tiny changes in volume can be accurately measured. Next, they say the reaction of 0.320 grams of the group 2 metal carbonate resulted in 89.0 centimeters cubed of carbon dioxide gas being collected in the syringe. And this is the equation for the reaction. We have the mass given here and the volume. They say determine by calculation the identity of the group 2 metal from this data. You must show your working and assume a molar gas volume of 24000 centimeters cubed per mole. Now here I began by using the volume of CO2 collected to find the number of moles of CO2. Moles of CO2 is going to be volume of gas, which is 89 centimeters, divided by the molar gas volume, which is that, and I got 3.7083 times 10 power negative 3. And then moles of the metal carbonate, because the mole ratio is 1:1, the moles are going to be the same, so they are the same as we got there due to the ratio being 1:1. So to find the molar mass of the metal carbonate, we will do the mass divided by number of moles. The mass is 0.32 divided by the moles we have here, and I got 86.29 gram per mole. Now to find the atomic mass of the group 2 metal, I have to get the total molar mass and subtract the component from the carbonate. One carbon is 12 and the 3 oxygens each is going to be 16, so 16 times 3 is 48 plus 12 giving us 60. So 86.29 minus 60, I got 26.3, and the closest group 2 metal is magnesium, so my conclusion was that is magnesium metal. So this brings us to the end of question 1. Let's continue to question 2. In question 2, bromoethane was prepared from the reaction of ethanol with sulfuric acid and potassium bromide. So we can see the equation for the reaction, and the procedure says in step 1, 10 centimeters cubed of ethanol was placed in a round bottom flask. In step 2, 10 centimeters cubed of sulfuric acid was added carefully and gradually to the ethanol in the flask. In step 3, 12 grams of potassium bromide was added to the reaction mixture in the flask. In step 4, the flask was set up for distillation and heated gently. In step 5, water, ethanol, and bromoethane were collected in a small beaker. In step 6, the bromoethane was purified. And in step 7, bromoethane was dried. I put these question marks when I was reading this question because I knew they could ask how and how. In part A, they suggest why the flask in step 2 was frequently placed in a stream of cold running water as sulfuric acid was gradually added. This is for cooling, and so this must be an exothermic reaction, so I say to cool down the reaction mixture since the reaction is exothermic and also ethanol is volatile. In part B, the potassium bromide used in step 3 was initially lumpy and not a fine powder. State the apparatus that will be suitable for breaking up the lumps of potassium bromide into powder. Here you use a mortar and a pestle to pound on it in order for it to be turned into fine powder. In part C, they say explain why an orange color was seen in the round bottom flask when it's first gently heated in step 4. The brown color should be bromine because this is sulfuric acid and there is a bromide ion, so there is going to be oxidation of bromide to bromine. So I said bromide was oxidized to bromine by sulfuric acid, hence the orange color of bromine was observed. In part D, they say complete the label diagram of the distillation apparatus used in step 4. So part of the drawing was given. They gave the reaction mixture of ethanol, sulfuric acid, and potassium bromide here. We have heat, and then that's the round bottom flask. I connected, placed in a thermometer, and then the connection entering into the condenser. This is a condenser. The cold water is coming in here, and the water that has been used for cooling is going out there. And of course, we have the collector here. So in part E, they say identify the solid particles labeled A in the flask that have been added to promote smooth boiling. These are called anti-bumping granules. We can see them in there. And in part F, they say bromoethane is very volatile. Suggest what could be done with a small beaker used in step 5 to collect bromoethane in order to prevent the loss of bromoethane distillate. Of course, we can place this beaker in ice cold water in order to cool it down so that it does not evaporate. In part G, they say describe how to use a separating funnel to remove the aqueous layer from the bromoethane collected in step 6. They've given us the densities of bromoethane and that of water, and we can see this is denser than water, so it's going to be the lower layer as the aqueous layer is going to be on top. So we will lay the separating funnel down, lay the 2 layers form, and then run off the lower layer, meaning the layer that remains in the separating funnel is going to be the aqueous layer, and the one runoff is going to be the bromoethane layer. So I say the separating funnel will show 2 layers. The aqueous layer will be on the top or on top, and the bromoethane layer at the bottom. Open the top and run the bromoethane layer into a new flask. In part H, they say state why the bromoethane would not be dried in step 7 by placing it in a warm oven. Remember, they've already told us it's volatile, so bromoethane would evaporate since it's volatile. And next they say a small quantity of water is removed by the drying agent anhydrous calcium chloride. Complete the equation by adding the formula of the product including its state symbol. When calcium chloride removes the water, it becomes hydrated. It has to be hydrated calcium chloride, which is a solid and written like that. And in part J, they say state a chemical test for the OH group in ethanol and a chemical test for the Br group in bromoethane. They want you to include the expected positive observations. For the OH group in ethanol, we can use PCl5 and misty fumes are going to be observed, or you could use sodium and effervescence will be observed. This effervescence is due to hydrogen gas, and these misty fumes are due to hydrogen chloride gas. For the Br group in bromoethane, use nitric acid followed by silver nitrate, and a cream precipitate is going to be observed. So this brings us to the end of question 2. Let's continue to question 3. In question 3, the equilibrium between iodine 1 chloride, chlorine, and iodine 3 chloride can be used to demonstrate the effects of changing conditions on a system at equilibrium. Iodine 1 chloride is formed by passing chlorine over iodine in a U-tube, and the equation for that reaction is like that. A further reaction then occurs between iodine 1 chloride and chlorine, which results in the equilibrium shown. So meaning the first reaction occurs between iodine and chlorine to produce that, and then this goes into an equilibrium reaction, reacting with chlorine to give us the iodine trichloride, and they've given us the enthalpy change for this reaction. The apparatus shown can be used to set up and then to demonstrate how the system at equilibrium responds to changing conditions. So we can see the setup here. There is chlorine that is going to be produced here. It will go through to the tube containing iodine. Our reaction will take place, producing the first product, which is going to be brown, and then this will react with more chlorine to produce ICl3. Here we have sodium hydroxide and so many more. So they say the addition of more liquid P to the flask on the left produces more chlorine gas. Explain the observations you would make as the amount of chlorine gas in the U-tube increases. Because both of these reactions take place in the U-tube, as more chlorine increases, we're going to produce more of this because this is a one-way reaction, so there will be a lot of this, and so the brown color is going to increase. However, as more chlorine increases, this also reacts with that, meaning this equilibrium is going to be shifted to the other side, and so we will see a yellow color. So I say there is formation of a brown liquid and then a yellow solid. Increasing chlorine leads to a faster formation of ICl, which is brown, and the presence of ICl and more chlorine shifts the equilibrium position to the right, so more yellow ICl3 is going to be formed. Next, they say the three-way type can be used to prevent more chlorine gas from entering the equilibrium system. Identify Q and state why it is necessary. Of course, chlorine is a toxic gas, so we need to use a fume cupboard. You can see here they're letting out some chlorine, so it has to go to the fume cupboard in order not to go to the lab where it could affect people. Explain what you could do to the U-tube to result in more brown liquid being observed. The brown color is this. To increase the yield of the brown color, since the forward reaction is exothermic, we need to increase the temperature to shift the equilibrium position to the left. And so I said, since the forward reaction of the equilibrium step is exothermic, increase the temperature of the U-tube to shift the position of equilibrium to the left, yielding more brown ICl. And part C says the sodium hydroxide solution absorbs excess chlorine. Write the equation for the reaction between cold dilute sodium hydroxide. Here they said cold dilute sodium hydroxide and chlorine, and state symbols are not required. Here sodium hydroxide reacts with chlorine to give us sodium chloride and sodium chloride. This is chlorate 1. This is oxidation state -1, and this is going to be +1, of course, plus water. So this brings us to the end of question 3. Let's continue to question 4. In question 4, an experiment was carried out to determine the enthalpy change of neutralization for the reaction between sulfuric acid and sodium hydroxide. And of course, we can see the reaction. The procedure is as below. 25 centimeters cubed of 1.25 mole per decimeter cubed sulfuric acid was placed in a polystyrene cup. The polystyrene cup was then placed in a beaker. A thermometer was used to measure the temperature of the acid and the clock was started. The temperature of the sulfuric acid was measured every 30 seconds for 2.5 minutes, and then 50 centimeters cubed of 1.25 mole per decimeter cubed sodium hydroxide solution was added to the acid in the polystyrene cup at 3 minutes, and the mixture was constantly stirred. This is very crucial when they add it so the reaction begins at that time. The temperature of the mixture in the polystyrene cup was measured at 3.5 minutes and then every 30 seconds until the clock reached 10 minutes. They say give the reason why the polystyrene cup in step 1 was placed in a beaker. This provides a wider base so that the polystyrene cup does not topple over or fall over. So basically it's for stability. So I say to make the cup more stabilized on the flat surface, preventing falling over. And in part B they say state the purpose of measuring the temperature every 30 seconds for 2.5 minutes. In step 2, this is to ensure that the initial temperature is constant before the reaction begins. In part C, they explain why the temperature was not measured at 3 minutes. Remember, at 3 minutes, they were adding 50 centimeters cubed of sodium hydroxide, and so there is no way they could measure since the temperature was changing. So I said because at 3 minutes, 50 centimeters cubed of sodium hydroxide was being added, the temperature was changing. In part D, they say the data from the experiment are shown on the graph. We have the vertical axis temperature, horizontal axis time, and they say determine the maximum temperature change, delta T, for this reaction using your graph. You must show you're working. So I drew a line through the initial values to give me the initial temperature, and then I'll use the other part to give me the final temperature. And then at the time when the reaction started, meaning the 50 centimeters cubed was added at 3 minutes, so I drew a vertical line there. In the other side, I drew a line of best fit through the data sets, ignoring these values. So this line and that line met at about 35. So meaning my delta T is going to be 35 minus 23. And so I got 12 degrees Celsius. And next they say explain why the temperature decreases over time. This is because the reaction had stopped. We're talking about the decrease here. The reaction had stopped, so heat was now being lost from the system towards the surroundings, so cooling occurred. And next they say give a possible reason why the temperature does not appear to change at various times, such as 5.5 to 6.5 minutes. This is around here. The temperature seems to be constant, and this could be that the change in temperature was so small that the thermometer used was not able to get a change. So I said the changes in temperature at those times are so small for the particular thermometer to measure them. State why the data will not result in the standard molar enthalpy change of neutralization being calculated. If we see here, they waited for the temperature to stabilize, and it was about 23 degrees Celsius, meaning this reaction was carried out below 298 Kelvin, so they're not standard conditions. So I say the ambient temperature is below 298 Kelvin, so the conditions for the reaction were not standard. And in part E, when calculating the enthalpy change of neutralization, the two expressions are used. Energy transferred is equal to mass times specific capacity times temperature change, and enthalpy change is equal to the energy transferred divided by the moles. Explain why it may or may not be valid to assume that the specific capacity of water is suitable to be used for this reaction. If we use the specific capacity of water, it may be invalid. That is because we are working with an acid-alkali solution. Of course, the specific capacity is going to be slightly different from that of water. So I say the assumption would be invalid because the acid and alkali solution used has a different specific capacity than water. And lastly, state why the number of moles of sodium hydroxide and not the number of moles of sulfuric acid is used in the calculation for this experiment. If we go back to the equation, this is enthalpy change of neutralization. And enthalpy change of neutralization is when 1 mole of water is produced when an acid and alkali react at 298 Kelvin and 100 kilopascals. So we see here they produce 2 moles. So the ratio should be 1 to 1. And so the moles of sodium hydroxide are going to be used because the moles of sulfuric acid are not going to be representative. So I said based on the reaction equation, 2 moles of sodium hydroxide produce 2 moles of water. Since the enthalpy change is based on moles of water, this should be moles of water are equal to the moles of sodium hydroxide. So this brings us to the end of question 4 as well as to the end of the whole paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.